we are ready to kind of look at the next concept with area. And I think you realize that we've thrown a symbol into this mix. It's called the integral sign. Of course, the integral sign means area, which kind of opens up the possibility for some rules. You know, I'm not a big fan of like rules, just like, hey, here's a rule. They really do have sort of a meaning behind them. So if you copy down number 1, number 2, number 3, let's just spend a quick moment talking about the meaning. Order of integration, A to B. Now, I don't know, have you really thought about this? Normally we go A to B, and you get an area, okay? Which again, each one of these problems has some type of area described by it. But if I go the opposite way, if I go B to A, now it's kind of like starting over here and then moving this direction. So if I go B to A, you might say, well, it's the same space. But you're going to find out with something either at the end of this lesson or on Monday that it comes out to be the opposite. So it's not the same. It's the opposite when I go in the opposite direction. Okay, so that's the order of integration. This one's, I hope that you look at that and you could have made up that rule. If I go A to A, I don't go anywhere. What's the area from A to A? That's not an area. Okay, so we have 0 for that. This one, it's one of those calculus common sense. You have a function, it's got a coefficient. The book called it a constant. I'm not really sure I understand that, to be quite honest. It should be a coefficient, but in any case, you'll find that there's some good times to like just pull that coefficient out of the integral. And what that does is allows us to just do the meat of the work right here without worrying about the extra number. But you can just multiply it at the end. You can just multiply it at the end and you end up with the same answer. Okay, so we've got some rules. They're also in the book. They are in the book, so if I flip this too fast and you didn't finish it, I hope that you take a quick peek back at the book, or you can also just watch the video here or take a picture. There's 2 other rules that I showed you on the other page. Okay, I hope that we can say that they also make sense. Okay, the first one's basically saying that even though it's not the distributive property, if you say that, we won't tell anyone, because the distributive property is when you're multiplying numbers. But what is true is that I can take the integral and I can separately do the integral of my f function and my g function. And if you add those up, you still end up with the overall integral. And then we get to the last one. I have a little star beside it because although you might look at it and say, well, yeah, that makes sense. That one, it's the one thing that I'm doing for a few minutes that might make you do a little double take. I'm going to adjust my sketch. The integral from A to B plus the integral from B to C. Okay, now again, yeah, the integral from A to B, that's like this area. The integral from B to C. Well, of course, you can add those 2 together and you can get the overall integral from A to C. Okay, so I'm not trying, there's nothing you're missing here. I can split it up is kind of what we say. But this will make for an interesting problem here in a moment when we do something with this. Okay, so these are like our 5 integral rules. Let me show you something that we can do with them at this time. There'll be other things that we do as we keep walking through the chapter. But we basically have a problem where I can give you the value of some integral. Now, don't overthink this. It's kind of one of those things where I'm just giving you that the integral of f of x, technically there should be a dx beside that. Did you catch that in my video, that is what makes this 2-dimensional? But the main thing here is the integral of fx from -3 to 2. From -3 to 2 is equal to -6. So again, that's a given. Don't overthink it. But let's say that you're also told that the integral from -3 to 6 of the same function, now it is the same function because it's still f of x, and we'll say that that equals 4. Hold on. I want to sketch that under each of these. It'll make more sense for us. Okay. I'm trying to help you see that behind each one of these problems is an area. Even though we don't really know exactly what the function is, okay, there is some function that has some type of area. Let me draw both of these. Okay, if you want to draw them, you can. Maybe you just kind of want to listen. I will say that the visual side to these is optional. It won't determine if you get the problem right, but the visual side will help you to understand more deeply what's going on, which obviously is what we're trying to do. So if somebody tells you that the integral from -3 to 2 is equal to -6, there would be some things implied by that. The main thing that's implied by that is there's more negative space. If you look at what I'm showing with this generic sketch, that's supposed to show a lot of negative area. Boom, it's a lot of negative area. There's still, though, apparently, there's still some positive area. Make sure that you understand that to say that the answer is -6 would just mean that these would be such that there's more negative than positive. Okay, but I could have some positive. I most certainly have some negative. Okay, the overall answer is -6. Now, if you go over to this one, understand it's the same function. So here's this negative area again, but this time I opened it up the whole way to 6. And at least it's supposed to be demonstrating to you that there's more positive area. I maybe should have made it a little bit bigger, but that's supposed to be more, which is why my final answer now comes out positive. Okay, now what can you do with this? As I did say, the drawings are optional, but it might help us to understand some of these questions, which is kind of like what we can actually do with this. And you'll see some of these problems in your assignment. They're kind of at the beginning. Now here's the thing, when you attempt to answer these, you're not allowed to use anything other than the given. So you don't go searching somewhere else, you don't make up some new information. So somebody says, hey, what's the integral from 2 to -3 of f of x? So, hey, do you see what changed? And it will be, it is kind of something subtle, but it's something that you need to notice. Okay, so do you see how it seemed to originally be -3 to 2? Maybe you didn't blink at that. That's kind of like A to B. But then I changed it to be B to A. I changed the order. So, if you change the order according to the rule, it should be the opposite. It should be the opposite. Now, soon, I don't know if it'll be today or definitely Monday, there'll be something we do where you'll be like, oh, okay, I see why you end up with the opposite. Right now, we're kind of just saying so because it's a rule, but there's another good reason that going backwards gives you the opposite area. How about, hmm, strange, hold on a second here, how about the integral from 2 to 6? Okay, now same thing, it's a good problem. I do notice what I did, and how can you use the given to find this answer? I don't want to give it all away, but make sure that you see that I'm now going just 2 to 6. Using my diagram, which I made to try to help you guys, using my diagram, it's like I'm now just asking for this section. Does that help you to use the given to come up with 2 to 6? Okay, now technically this is rule number 5. As we said, rule number 5 is basically saying that I can break it up. Seems kind of obvious, right? You can break it up, but what happens when you actually have to use it? Let's sort of give some of the popular answers. One of them is right. Maybe you got -2. Maybe you got 2. Maybe you got 10. Maybe you got -10. One of those is the right answer. What were the options again? 2. Anybody get 2? -2. 10. There's a couple hands going up. -10. Okay. Well, the ones that voted, you are correct. It does come out to be 10. And I'll be honest, I don't want to overdo this, but sometimes because like I don't see it. Actually, it was one of those. I'm like, I don't see it. I just kind of like struggled with this until a student showed me kind of what's really going on here to kind of keep it simple. Because what's really going on here is that you could change this problem to be such that we know that -3 to 2, that's kind of like, going from here to here, A to B, and then pick up where you left off, going 2 to 6, pick up where you left off, would have to equal the whole thing. Now, the whole thing would be -3 to 6. Okay, so if you just kind of keep it simple, it's like we're going A to B, then B to C, and then that's the same as the whole way, A to C. Now, if you take these integral signs and you kind of change them to just be a simple equation, it's 100% true that the first part of my equation is -6. It's also 100% true that this is what I'm trying to find. Make sure you realize that we don't know it, so we could call it x. And well, the overall answer, or I should say the full integral, is equal to 4. Now, I know everybody knows how to solve that, but that is good proof as to why the integral is 10. Obviously, x is 10, but what that really means is that this integral is 10. Think about it visually. I need a whole bunch of space right here. I need a whole bunch of space to kind of counteract this negative space so that my whole answer, my full integral from A to C, can come out to be 4. Okay, so even if you think about that number, it's supposed to make sense. Let's do one more of these kind of rule problems. Just going to squeeze it down here. How about the integral of -1/2 to 2 of f of x dx? So we're doing the integral from -1/2 to 2. Okay, negative 1/2 is probably somewhere around there. So it's like we're trying to find this and this. So we're trying to find those. If this problem's bugging you a little bit, that could be good. It would depend on how it's bugging you, but if it's bugging you where you feel like you wouldn't know, or you wouldn't be able to determine, that's a good bug. You can't just say it's half a -6. You can't just say it's half a -6. I don't know what kind of function it is. I don't know if my function's like a consistent rectangle or triangle. I'm trying to show you that the function could be doing anything. So who knows? Who knows if I go here to here? Maybe it bounces out to be 0. Maybe it's still something negative. But you would not be able to just say, and this is like a made-up rule, that because I go half of my interval, half of my A to B, that I would end up with half my answer. Because again, it's visual, and it's a function. And of course, functions can vary. So this one would sort of be like not enough information. But the main point here is we don't want to make up a rule. There's no rule that says half the interval is going to be half the area. Okay, it's kind of a peculiar little topic talking about these rules, but there's nothing else really to do with them except that when we see some problems with integrals, we can apply these, which I'll show you, or we can do some of these little given problems. What I would like to do is I'd like to give you a sneak peek at kind of the place that this is headed. And we've said it a little bit, but we've never really officially showed you how. But we've said it a little bit that basically an antiderivative is somehow connected to an integral. I'd like to show you that in a little diagram. Okay, it's good that we just have some time right now, that we don't have to rush through this, because I want to just give you some time to think about what I'm about to show you. Integrals are connected to antiderivatives. Now, if you back up with me a step, I want to make sure that I draw this the way I was thinking. If you back up with me a step, we have learned about some things you can do with a function. I'm talking about the big picture this year. A function is an equation, a function is a graph, and it has a derivative. If I do the derivative of a function, I hope you haven't forgotten about that, have you? If you do the derivative of a function, of course you get f prime of x. Make sure you realize that I'm not showing you something new, but I'm trying to take you back, or I'm about ready to show you a little connection. Okay, and of course you can do all kinds of things with that derivative. You can find slopes, concavity, and other fun stuff. Now, you have had a taste, we haven't spent a lot of time with this, but you've had a taste that I could start with the derivative. Now follow me here. I could start with the derivative, and I could, with an antiderivative, make sure you read what I'm trying to write here. With an antiderivative, I could like go back to where I started. And we did a little bit of that. You may remember actually at the end of the last chapter. So here's the new thing. An antiderivative doesn't have to be just between these two functions, kind of like a bouncing ball back and forth. I can actually go one more step backwards. I can go one more step backwards by doing an antiderivative. Now, you could think of this as the function that came before f of x, although that's not really how you have to think of it, but I more just want you to realize that I can start with f of x and I can still do another antiderivative and create a new function. Now, that new function has to have a name, and math is good at coming up with creative yet simple ways to describe new things. So check this out. This function will be described as capital F of x. And it's kind of strange when we say it verbally. We either have to say capital F of x, or we just have to pay attention when it's written down. But if you see a capital F of x, we're talking about the antiderivative one step more in that direction. Now, what is sort of the big deal about capital F of x? Well, you probably won't be shocked when I tell you that capital F of x is able to help us. It's going to help us to get the area, which means it's going to help us to evaluate an integral. Now be careful, I didn't say capital F of x is the integral, as that actually wouldn't make sense, because an integral is a whole process of finding the area. But I am telling you that capital F of x is going to help us to determine these things. Okay, and the way that it does, so we're going to sort of give the big reveal here. The way that it does is actually with a simple subtraction. I want to leave you with this here on this lesson. I don't want you to be bugged that I'm not going to show you. I just want you to be ready when you come back that we will do this. But it's a simple subtraction. As it says up here, it's the difference. Difference means subtraction. It's the difference of this capital F of x evaluated at A and B. Now, what's written up there in a little sentence is shown here with this notation. If you highlight things in your notes or somehow make a big deal out of them in your notes, this would be one of them. Okay, because this gem right here, this formula, well, it's pretty big. You'll find out just how big next time we get together. So the integral of f of x from a to b is capital F of b minus capital F of a. Okay, it's pretty neat. I don't want to just hurry up and do something with it. We'll have plenty of time next time we're together, and you guys, I hope you're able to come, because it's neat. Yeah, it's sort of one of those wow moments.